All right, so number 26, calculate the final temperature, right? So that's obviously what we're looking for. And we have 980 microliters of acetone. Microliters is a volume, right? Which means not a mass. And it's initially at 23.2 degrees Celsius, and it absorbs 13 millijoules of heat. And then it gives us a density, oh my gosh, which converts between, ding, 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 mass and volume. And we also know the specific heat of acetone. And again, you're not expected to memorize specific heats outside of water. So now we just need to strategize, right? First, we're going to take our volume, and using our knowledge of density, we can convert that volume to a mass, okay? Again, chemistry is cumulative. These things come back over and over and over again, right? So make sure you know how to do this step. All right, so once we take our volume and we convert it into a mass, now we can take that mass and plug it into the Q equals mc delta T. Now, here we have to be mindful, if we're solving for T final, really the easiest thing to do to ensure we do the math correctly is to go ahead and solve for delta T, all right? So that's the first thing that we're going to do, and we're going to go ahead and isolate that delta T variable to make sure we're less likely to make weird mistakes between our multiplication and division, right? So we're going to take that Q and isolate that delta T, and now we're going to plug in our pieces and solve for delta T. So we'll start with our Q, and don't forget we got to take that millijoules and convert it into joules. Yes, it's expected that you still know those prefix conversions. And then we'll plug in our M and our C value, and then we'll go ahead and solve for our delta T. Obviously, when we set this up correctly, we should notice that all the units cancel except for degrees Celsius, because that's the appropriate unit for delta T. Okay, and then obviously now that we have our delta T, we'll go ahead and plug that into the delta T equation, which says delta T equals T final minus T initial. So we've got the delta T, and we'll put that in the appropriate place. We already know T initial, and we'll put that in the appropriate place, and then we'll solve for T final. In this particular instance, it turns out that my delta T is so small, based on significant figures, that T final is the same as T initial, right? As in, if I added 23.2 to 0.006986, I would still get 23.206 something, which is the same thing. Yes, based on significant figures. All right, now moving on to the next one. So now looking at number 28, which is very similar to the one we just solved. So it says that we are looking for T initial. So what temperature did we start at is our goal, knowing the mass of water and the amount of heat absorbed, which is our Q. And we also happen to know the final temperature, right? So just like last time, what we're going to do is we're going to set up our Q equals mc delta T expression, and we're going to isolate delta T and solve for delta T first, right? That's going to help us avoid weird mistakes. And then once we've isolated our delta T and solved for it, then we'll plug that back into our delta T expression. So now that we have our delta T, we're going to plug it into the delta T equals T final minus T initial, where our delta T will obviously go in the delta T spot. Our T final, which is 77, will go in the T final spot. Now here, this is where it's important to pay attention that the problems are similar but not the same, right? So for example, if we once we subtract that T final, right, because the goal is to get T initial by itself, right? If we subtract T final, what we're going to end up with is a negative number is equal to a negative T initial, right? So don't forget your basic math rules here, right? In that, what that means is you basically multiply both sides by -1, right? Which cancels out those negatives. Don't throw away all of your basic math stuff that you know, yeah? Okay, and moving on to the last one, here we're gonna do number 32 together. So this one is kind of like a couple of the EOCs. It's kind of like what was in the gizmo, where we have a mass of beeswax, and that beeswax has its own T initial, 10 degrees, and that beeswax at 10 degrees is added to a known mass of water, which is initially at 24 degrees, right? So if we think about what that means, we have 10 degree wax added to 24 degree water, which means that the water is going to give heat to the wax. There's going to be an exchange of heat, right? And everybody ends at the same T final, right? Because that's what we've been talking about, right? When those molecules collide over and over again, they end at the same average kinetic energy, which in this case is marked by 20 degrees Celsius. So if we're trying to find the C of the wax, what that means is we have all the information we need to solve for the amount of heat from the water. Yes, we can solve for the heat of the water. We have T initial, T final, mass, and we always know the C value for water. So step 1 is to solve for the Q of water. Now here is the key to this problem. If 33,000 joules of energy are released from the water, they go into, flip the sign, the wax. Yes, key. The heat that leaves the water is exactly the amount of heat that goes into the wax, right? Which note that we symbolize that with the different signs. Now we'll take Q wax and we will set up Q equals MC delta T for the wax and solve for C of the wax. Yes? All right, so then we're just going to have to take the now we'll use the wax's information, including its mass and its Q and its delta T. And now the last step is to round to the correct number sig figs, which should really be 1 based on the delta T for water. And that's it. We have solved for C of the wax. Thanks for listening. Be good, and I'll see you soon. Bye.